Hello everyone and welcome to the first session of today of our Digital V-Days. Yeah, I'm very happy to introduce the topic of today with ESD and also to welcome my colleague Christian Koch, who is working as Field Application Engineer at Würth Elektronik. Christian, hi.
Hi.
Nice to do the webinar together with you.
Yeah.
So, my name is Markus Eberle and I will moderate this webinar today. And so just a few information from my side before we start into the topic. So you will be muted during this webinar, but you always have the option to ask us your question on the chat. And then later on we have a quick session also for the live Q&As. And if we can't answer all your questions there, we will answer them later on via email. So you will also get all the informations, the recording, the slides later on from us by mail. And now, I'm happy to give it over to you, Christian, and have fun.
Okay, so then let's start with the topic of today. Hello everyone from my side. As said, my name is Christian Koch. I am FAE in the area of North Germany. I guess that's okay for my person. So let's start with the topic. Topic, as mentioned before, today is ESD. As we don't have that much time, we are limiting it a little bit on some focus points, and let's start it. So what is ESD about? ESD at the end is nothing more, as we can say, we have amount of charge that is generated or separated by contact and separation of some materials, in general mostly insulating materials, and therefore the more often they touch and be separated, the higher the charge is that is generated, and at the end it leads to high voltages. Those high voltages can cause main failures in electronics, just because of the point if we then touch somehow any conductive mechanics or circuitry, our device under test, maybe our own product at the end, then it can cause damages on structure of semiconductors, and that at the end leads to main failures. And this is what we want to avoid. And let's go on as we talk about voltages. Which voltage levels are available? We have a small overview. I guess many of you know this kind of overview, but just for information, I guess the main example we see all often is walking across a carpet, and therefore we see about 35 kV is possible as voltage during winter time. Less air humidity at the end is their high voltages can occur during the summertime. With high air humidity, voltages are much lower, but we all know it in the winter time. If you come to the office, most of the time if you touch a doorknob or whatever, a spark is flashing over, and at the end this is the main reason or the main point we want not to occur. So we want to avoid it at the end. And there's the question how to avoid it, and what measures can we do, or what can we do in general against ESD? And we have separated it in, let's say, two chapters. First of all is external measures. And external measures are at the end nothing more than ESD protection area. You all know it from production lines. You have special floors, special clothes, special shoes maybe, or even behavior control. That means you are not allowed to bring everything inside this area what you want to. But at the end, everything is prepared for the point that no high voltages arise at any point, at any device, whatever. Also included for ESD protection is protective packages. That means you are not allowed to take any paper, carton or whatever. It must be a special ESD package for just delivering the parts into this area. All this is done on external measures, but we want to focus today on the point, what can we do on the PCB side? And on PCB side, I guess you all know it, we have the possibility to put some transient voltage suppression devices on it, so overvoltage protection on a PCB board itself. And therefore there's the question, which one is the right one now? What to use and what to take onto the PCB? And there we want to have a look at today which part is the right one for your application maybe. But if to choose the right component, we have to check before what is our enemy. And yeah, what is our enemy is given in the law. Let's have a look at the basic standard. It's the 6142. And therefore it is given that we have conductive pulse, we have and pulse applied on our device via air gap. But how is the pulse shaped? And that is also shown in the law, in the basic standard. And there we see that the pulse is having some special behavior, let's say it like this. We have a rise time of about 1 nanosecond, and that is roughly in a frequency range about 1 gigahertz. We have the pulse width. This is about 30 to 60 nanoseconds. So again, high frequency content is inside. Yeah. But it's not only about high frequency, it's also about high voltage levels. We've seen it before, 35 kV is possible, maybe. Yeah. But here for those testing levels, we have for contact discharge, as you can see over here, we have 2 kV, 4 kV, 6 up to 8 kV, and even special. So higher classes are also available. That depends on where your device is used. So this depends, then you have to look at the law, which of the levels is responsible for your device. But at the end, it means you have applied on your device some kilovolt impulse with high frequency content. And also, if we have high voltages, for sure, if we have a direct short through ground, it will be a high current in this time. Yeah? And at the end, this is the problem. But if we want to know what's going on during the test, because the test, let's say, is the worst case scenario, we try to have maximum impact on the circuitry of our device. So we want to stress it a little bit. But what's inside the test generator or the ESD generator can easily be seen here. We have simply set one capacitor that is loaded by the test voltage 2, 4, 6, 8 kV and via RC, and over RD it will be discharged if we trigger the switch in front of the test generator. But if you now have a look at the bottom line, over here you see for human body model, it's about 150 picofarad, our capacitor, and our discharge resistor will be about 330 ohms. Could be more, could be less. At the end, it's let's say it's the mainly value for capacitance that a human body will give through the environment. Also, RD with 330 ohms is a typical value of discharge resistant. Surely it depends on how the contact is done. So if you touch the doorknob by the complete hand area, or is it just the fingertip that is doing the contact? So let's say it can vary, but those two values are given by the law, and we have to take care that our device is able to handle it. Short hind, just the discharge via the contact is not everything during this pulse. We also have, let's say, field happenings or field coupling events that will occur during the ESD event, and that will be a problem too. And therefore, we have to ensure that our circuitry is working well. So we know the current pulse or the shape of the pulse, we know already. We know there's a high voltage level, and we know that it will bring some problems in our circuitry. The question now is, what problems could arise? As said, field coupling, so H field, E field will be a problem, but also the back path of the current will be a problem in your circuitry. And just to give it a little example, we have here two, let's say, semiconductor ICs. They are both connected on one ground net, and the ground net is not done properly. Let's say we have a strip line, and for strip lines, we all know there's the rule of thumb about 10 nanohenry per centimeter. And let's assume we have both of those ICs separated by 10 millimeters, so we have exactly 10 nanohenry parasitic inductance on the ground net. And therefore now we have some, let's say, some typical input capacitance of 5 picofarad, just because it's calculating very easily. So, and therefore we have our 2 kV impulse that is applied on those 5 picofarad with a rise time about 1 nanoseconds, and that at the end means we have a current, inrush current, roughly about 10 amps. And if we now take those 10 amps and apply them on those 10 nanohenries with the rise time of 1 nanosecond, we will have a voltage potential about between these both 2 points about 100 volt. That means one of the ICs is floating up on a potential of 100 volt. That means at the end one of them will have any failure, main failure or internal destruction at the end. So this is the problem we don't want to have on our PCB. Just a few sentences for this calculations. It's done with ideal components. We know the value would be a little less than calculated in here, but just to give you a roughly idea, I guess it's a quite good example. Okay, we know the impulse, we know the voltage level, we know there's a big current flowing, so we know we have problems on our PCB. Now there comes the point we have to choose which part is the best part for our application, and therefore we have to say there are plenty of parts available in our portfolio. You have to choose, you have the choice, and the question is where you have to focus on to take the right part. Therefore we have a short overview with, let's say, parts that are available in this area, and let's start with our TVSP, our power TVS diode. It's more or less overvoltage protection for DC applications, but also it has an impact on ESD purposes. You can use it at the end. If it's TVSP is standard package size, SMA, SMB, SMC, that's what you know, as you know it in general, they are available. If you want to have it a little bit smaller and more I/O pins in one package, so more channels that being secured over here, you can take our VEA or ESD suppressor array. And in this case, it's not a TVS diode, it's more or less a micro varistor. So we have here a real varistor array in this case. On the other hand, we have the big area of TVS diodes, and as you see here, several packages, DFN, SC, SOT, DFN in a long range version, so for more channel application, and also MSOP with 10 pins, with 8 pins. So there's a big variety. You have to choose what are the right criteria, we will see later on. And last but not least, our VE series, our ESD suppressor as single version, down to sizes of 04, 02. That means at the end, if you prefer single security of your data lines, you don't want to put ICs because you're more familiar with that kind of layout, then you also can take those ESD suppressors. We will see later on where you have to look at which criteria to choose the right one later on. Yeah, so if you see it above, VE TVS diode, standard, high, super speed series. We have 3 different series, and now we just have to check where are the differences of those series. And so let's start with the standard series. And there you see one big point. They are available in unipolar and bipolar. This is the only series where this option is available. Why? Very easy said, because in this case we have in every IC internally we have separate TVS diodes per pin. So on every I/O pin there is a separate TVS diode that is working against ESD, and this one we can choose as a bipolar or unipolar. At the end, it's the standard series for, let's say, low speed application or DC distribution, because we have, let's say, quite high channel capacity up to 12 picofarad. From 12 picofarad up to about 1 nanofarad roughly. So it's quite high channel capacity. But for low speed application, absolute a good choice. As said before, many different packages available, but let's focus on one package, DFN 6010. Why? Standard series, yes. Unipolar or unidirectional, bidirectional available, Yes, but what is the point on this package? It's a TVS diode, but it's also referenced for burst and surge. You can have a look at it in the data sheet. There you will find data given even for those overvoltage events. So quite small. It's a quite good device against TVS, burst and surge. So just have a look at it for DC application for sure. Yeah, so these are the informations regarding standard series. Now we have to check what is the difference related to high speed and super speed. So one point is, we have said it before several times, one point is the channel capacity, as we are talking about super speed. Or let's first begin with high-speed series. For high-speed series, channel capacity is about 1 picofarad to 3 picofarad. And for super speed, we are about in an area of 1.2 to 1.6 picofarad, so even smaller channel capacitance. But what now is the main difference in internal structure? You see it here. In this case, for high-speed and super speed series, we just have one big overvoltage or one main overvoltage protection device, always shown in the middle of the IC. And the rest of those diodes that are connected to the pins are more or less rectifier diodes that will forward the positive ESD impulse directly through our overvoltage device. And the negative impulse will directly redirect it through ground. So it's directly through ground, and we are out of this impulse at the moment. But now we see that there is another pin, pin 5, so the VDD pin. So what is it good for? And as you can imagine, we would here put DC voltage on, so our rail voltage, and at the end this brings down again the capacitance of our main overvoltage suppressor, so our device can react much faster. So if we give our device more power against ESD by putting VDD on pin 5, then there comes the question, what is now this diode good for in this version over here? So let's assume you put together two devices via an USB connector, and maybe one device is already powered, the other device is not powered yet. That means one device is already sending signals through the data lines, and if the second device is not powered, my VDD would be 0 volts. And that would mean that all the data would be redirected through VDD to feed the internal capacitor of the net. And that is something we don't want to have, we want to avoid, and therefore this diode is built in several of them. You can choose, just have a look at the data sheet. It's an option, it's not a must. It depends on your circuitry, on the behavior of your device. But you can do it, that's for sure. Okay, so these are the main differences between high speed, super speed and standard version. And now the question comes, when to use or what part is suitable for which kind of bus type. And therefore we have this short overview from our website, from our web page, and there you see some hints in the list. And over there you can easily see recommendations, which is the best version of bus type for this TVS diode. And at the end it means, if you don't know really which is the best part, how should I choose it, have a look over there, and then you have some kind of reference what you can use, and you will see the parts what are the best for your application. So just go on web page and check it out, and then you know the best version for your case. Also, we talked a lot about channel capacitance. Therefore, you see it's given here. You have an overview, what is the typical channel capacitance, so you can roughly estimate what is the best part here for my application. Always a good point to see, to get the right choice over there for your product. Okay, so we talked about channel capacitance. We've seen before many internal structures, but at the end, what are the points we have to consider for using or for choosing the right TVS diode? And this we can see over here. So we have a little list for TVS diode selection, and it's about 4 points here in this case. And point 1 is, as seen before, channel operating voltage. So if you want your device to work properly, you have to take care that the channel operating voltage is suitable through your normal voltage on your device, or bus level voltage at the end. Why is it that important to know it? Because if you see above, here we see the breakdown voltage of the device. That means if you have a 5-volt level on your bus or on your signal, whatever, then you have to take into account above a voltage of 6 volt, your diode will draw a current. That means you will have an impact on your signals, and you don't want to have this point reached. So therefore, take care about channel operating voltage. It's very important. First one. Second one, we've seen a lot, channel capacitance. We've talked about it during the several series we have. And over here now you see we have 2 of them. We have 2 input capacitance values, and that's for a reason. We have the normal value, the C channel, the channel input capacitance. That's for, let's say for single-ended signals. So signals reference to ground, I2C, SPI, all this stuff. There this capacitance is relevant because it's the load of the driver of your bus, and the bus driver has to handle this capacitance. So you have to take care that signal integrity is given. So therefore this value is very important. If you now switch over to, let's say, differential pairs, also to differential signals, there you have the problem that you have 2 I/O pins that are responsible for your bus. So there it is important how big is the capacitance between 2 I/O pins of my TVS diode. And this is the value given here, channel to channel input capacitance, so C cross. So if you have differential pairs, you have to look at this value. As a rule of thumb, you can estimate it if you take the normal channel input capacitance and divide it just by 10. Then you almost get the value for the C cross value. But both of them are very important. You have to take care about them. As we speak about, or as we spoke about signal integrity, we also deliver for the high speed, for the super speed series, the insertion loss of the TVS diode. At the end, it's the attenuation that is given by the capacitance of the diode. But anyhow, if you want to know on which frequency range you have what for an impact on my signal, you can have a look here, and therefore you will find the right value. So you have to check that the attenuation on your bus frequency is not that high, so your signal is already in a good shape and signal integrity is already given. So therefore you have the insertion loss of the TVS diode. And last but not least, clamping voltage, also an important point. As we talk about high voltage impulses and our diode has to react on them by drawing a current, there is the point that we have a voltage over our diode, and at the end this voltage is given here for the clamping ESD voltage level, and there you see for an 8 kV impulse with 16 amperes we have a clamping voltage of 10.5 volts. That means all the circuitry around your bus must be able to handle those 10 volts. If not, you will have a damage in your circuitry, even if you have those TVS diodes into your PCB and everything is routed fine. But you have to take care that your circuitry is ready to handle this kind of voltage or this voltage level. This is always also a big point you have to consider. Okay. So we have spoken about TVS diodes, we have spoken about the criteria of TVS diodes where we have to focus on, but we've seen before that there also is the availability to choose single overvoltage protection devices, so normally varistor sizes or varistor techniques, and therefore we have, let's say, several series with different with different given parameters, and therefore we want to have a look at it. And the first series in this case is our ULC series, so ultra low capacitance. And here you see all of them are having a channel capacitance of 0.2 picofarad down to sizes of 0.4, 0.2, so very small in dimensions. So if you really like to make your ESD protection on single channel purposes, then you can use this one. If you're familiar with that kind of, let's say, layout, then this one is the right one to choose. If you really need low capacitance values, we are here in the area of the SuperSpeed series. If this is not enough, we have the Fem2F series, also down to 0.4 or 0.2 as package size, but here we have a channel capacitance of 0.04 picofarad, so even less than for the SuperSpeed series. So if there's any special requirement on your circuitry, here you have the right overvoltage protection device. Just have a look at it on our webpage. You find everything, all the informations about online. Yeah. And now in this case, also last but not least, standard ESD suppressor series, so SMD varistors, single channel varistors at the end. If you would like to work with those parts, here they are, also available down to sizes of 0.4, 0.2. At the end, you only have to consider that we here have, let's say, a little bit higher channel capacitance values. We see it over here. I just focused on 0.6, 0.3 just for an example. And we see over here that we have channel capacitance about 100 picofarad. So low speed application, DC distribution, voltage distribution is the right application for those parts. But we have special parts over here with channel capacitance about 3 picofarads, and these parts are even suitable for USB 2, LAN, 100 megabit, all this stuff. So it's up to you. It's your choice which kind of layout you would like to do. And therefore we have the parts, and it's your choice what is the best. Where does this high capacitance come from? Just as at the end, it's simply said the inner structure of those varistors. We have a multi-layer construction, and therefore we have several of metallic plates that are standing against each other, and they are building a quite high capacitance value. That's all. But as seen, you can choose which capacitance value is suitable for your application, and therefore you just have to choose the right version with the right size and the right voltage. Okay, so far so good. So now we have spoken about the parts. We have spoken about the ESD parts itself. We have spoken about criteria, how to choose the right parts. But all this stuff has no importance if we don't know what happens during the inrush current or during the ESD event. And we should know what happens in the MC house. And therefore, we have this little, let's say, picture of a device under test. And therefore, we have a connector, we have our TVS diode, and behind this TVS diode, we have our circuitry. And now we put in the plug, and therefore we see maybe some ESD event can occur. For sure, some noise will come in, will come out, but we will focus today on TVS, so ESD purposes. And what happens now is that the TVS diode is working hopefully quite well, and most of the current is drawn out of the I/O lines and given through the ground plane. What now happens is that all the current is flowing underneath our circuitry. And you remember we talked about 1 nanosecond rise time, about 60 nanoseconds pulse width. That means we have high frequencies going on our PCB, and we don't want those high frequencies to be in the near or the closer range of our circuitry. So therefore, what would be the best option? The best option would be not to have this current on your PCB in your circuitry. So if you can choose it the better way around, just redirect the current as quick as possible in the shortest way through your chassis, so that if you have a conductive chassis for sure, so that you don't have this current on your PCB. So now this picture now, wants us to know that, well, gives us the information, forward the current through the protective earth cable and everything is fine. At the end, this is not true, because we have to see what's going on in the EMC chamber. As we talked about high frequency content of this impulse, that means that our protective earth cable is not suitable to carry those high frequencies. It's simply high impedance for this impulse. But let's have a look what will happen, or what is the ESD test setup in an EMC lab. And therefore we shrink our PCB and have a look at what will be in our lab. And therefore we have a table. We have two conductive planes, one on the table, one on the bottom. And as you can see, our ESD generator is referenced to the bottom ground plane. And this is the point you have to consider. Because what now happens is that we have to think about the impulse. And as said before, the impulse is simply said high frequency. That means, on the other hand, now we have internal capacitance that is loaded, that is discharged through our device. And now this circuit simply wants to have a short just to get back the charge, to recharge the cap or to equalize the cap, better said. So what happened now is that we have capacitive coupling from our device through the plane on the table, and from the plane on the table it goes to the bottom plane. So this is the current path you have to activate somehow by any capacitive coupling that is possible. The rest of the voltage that may occurs in your system will then be driven out by time over protective earth or over the normal cables for power supply. But for ESD event, this is the circuit or the current loop you have to take care about, and this must be set to secure your device. And to have this on, let's say, on the PCB level, we have brought two examples here, and those two examples are a little bit different. So we have taken them out from two of our demo boards, or let's say from our EMC sticks we have for USB-C. And let's switch to the first example. Maybe some of you already know this. It's our USB 3.1 Type-C filter board. It's, as said, a filter stick. You can put them into the lines, and the big benefit is here everything is given. You have your common mode chokes against EMI purposes. You have your line filter. This is already suitable for a power delivery mode. It's for 60 watt and for 100 watt suitable. But today we want to focus on ESD purposes. That means for us it's important now from the whole board this area with those diodes over here. And you can see, or you can already imagine how the layout is done. As short as possible, as direct as possible, and directly referenced to ground our TVS diodes. Let's have a closer look. There you see those diodes. You see all the 3D bodies from our parts. Let's get rid of them and let's say, okay, this is a quite nice picture, but we want to see into our PCB. So let's get rid of the solder resist and even get rid of the core of the material of our PCB. And therefore we see how it is done. In green, below the bottom or below the top traces, we see a complete ground reference plane. And we see that all the lines where our diodes are sitting are not routed in a different way. That means we have over here impedance controlled signal lines, differential pair routing, but the PCB was customized in a way that the distance between the lanes, between the traces is exactly the distance for our pins. And at the end, this means we have no impedance jumps on our lines, and we can directly put our TVS protection devices on the lines with no rerouting, no impedance jumps, directly put on the lines, and they are referenced directly through ground. This is how it is done over here. Just a quick note. You see over here, one pin is missing. It's a fault in the 3D bibliothek, but the security here is given because here in reality would be a pin, and we have both data lines secured and directly referenced through ground via this pin. So as short as possible, as direct as possible is the goal, and then for sure the next goal is to put the current directly to the ground plane, get rid of this ESD current. This is something you have to consider in your layout. So as this is for, let's say, general purposes, we have the big ground, or one big ground underneath our PCB. Let's switch to the second example. And the second example is, let's say, more industrial application. And it is also given by one of our colleagues. And here we have our gigabit Ethernet front end. And as you can see, we have it in two different ways. At the end, what do we have here is, a connection board between Ethernet, gigabit Ethernet, and USB 3.1. And let's say the long connection cable would be the Ethernet connection, and therefore we have a special ground system here in this board. That's why we say, okay, industrial application view, because we don't want any current, any low frequency current flow on the ground through our chassis, but we need our ground, we need our chassis for safety purposes, and that we will see over here. As said, we have a discrete version, we have a version with integrated magnetics, and therefore you see it over here. This is the integrated version, it's much more smaller, and the discrete component version has the LAN transformer here on the outside, and therefore it's not an RG45, it's a so-called modular jack. But for EMC purposes or for ESD point of view, we stick on the discrete version because everything is stretched out and we can have a much better look at the inside of this board. If you want any further information about those two boards, you can have it on our reference design note 16, on our application note 116, and you have the possibility to download the Altium files of both of those two boards. So you just can review all the stuff you see here. That's no problem at all. It's on our webpage, just check it out. But for ESD purposes, let's have a look at the board. And the board in 3D view in Altium looks like this. And there you see what I said before. We have divided ground plane at the end. You have here the chassis ground plane, or the ground of the connector. You have the ground of the circuitry, and even for USB purposes, it's even divided. But the big point is that chassis ground and internal ground are divided and not directly connected. But anyhow, we need some kind of ESD protection devices on our boards, and they are there. You can't see them at the moment, so let's switch the board, or flip the board better said. And here you see that we have those TVS diodes directly underneath the data lines. So it's more or less the direct way over here, but just take the bottom side of the PCB. But if we already get rid of everything that is behind us and the top layer, let's put out the board itself. Then we see that we have over here our connector. Now it's red and red, it's a little bit tricky, but I guess we can see it. Now we have over here our connector, we have our LAN transformer, and over here we have our TVS diodes. That means if we have a direct contact ESD impulse, most of the time the test setup will hit the chassis of our connector. Therefore, the ESD current is drawn through this ground plane, through the outer ground plane, and therefore we can directly forward the current through our chassis. No problem in the inner circuit. But if there is a little bit of energy left and that has passed through our pins, that means we have an ESD event on our data lines. At the end, our transformer will somehow couple some of this energy out, and there we have our 2 kV capacitors up to the chassis ground, so there will be a little bit of this energy will be drawn out. And if then the rest of the energy comes really through the inner circuit and we have it on the secondary side of our LAN transformer, then here the TVS diode gets active directly on our data lines and can reward or forward the current directly to chassis ground. And therefore it's not seen here at the moment, but we have also big ground plane in the between layers. There are 2 additional ground planes, and therefore we draw the current directly back to chassis ground. And this is only possible because here we have some coupling caps over here and over here, and they are there, let's say, well equipped, so just to support this kind of event so that the most of this current can be drawn out of our system. Okay, so let's get the bottom side again seen here. So now you see that we have our TVS diodes directly on the bottom side, and the current is going directly on the ground, on our internal ground, and then will be drawn out on chassis ground. So therefore we can reactivate this capacitive coupling to the environment, and this is the point where we have to focus on regarding ESD. Okay, so we have seen how to select the diodes. We have seen that there are plenty of versions are available. We had a look at the ESD test setup, and now we had a look again into some design examples and how to route everything. And I guess that's enough for today. And let's finish with some, with a few sentences. Please remember, yes, if you want to fight against ESD, you need overvoltage protection device, but it is not everything you have to take care of. You have to take care about the whole measurement setup, and it's very important to remember that your layout, the structure of your device is also important here in this case. Everything has to fit together so that your device gets ESD resistant. Okay, so that is the main focus point you have to remember.
Yeah, thank you, Christian, for the interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from the presentation. Now you can download it on the right side, and then I think you can start. Christian, can you hear me?
Yes, I'm here.
Perfect. Okay, then I think we can start. First question was about slide 6. What about test generator? Is it only possible to test HPM?
So we just mentioned HPM, so human body model, because this is most of the time the model that is used, because most of our devices are handled by human. So but no, the test generator can handle several kind of models. Most of the time it's kind of cartridge system where you just can pull out the inner structure and put another device on it, and then you are ready for another testing model. But this simply depends on the law that gives you according to how to use your device. So therefore you see which kind of model you have to use. But yes, the test generator can handle different kind of those models.
Perfect, thank you. Then, next question. Can cardboard become electrostatically charged? Are cardboard boxes safe inside the electrostatic protected area?
So as I'm actually at the moment don't know what a card box is, I can't really answer it. So if you're with some kind of your box, if you are in your ESD protection area, it could be charged. If it don't have the right technical needs for it, so you have to have a surface resistant box or a surface resistant material so that the charge can be guided through the protective earth. That means if it is made out of the right material, then it would work. If not, you really can charge up your box. But at the end, I don't know exactly what is meant with card box. So yeah, maybe the guest can write us again what it is meant.
He writes it means cartoon, so card boxes.
So
carton, in
yeah,
German,
so
carton.
it's made, okay, so it's made of paper. So simple carton boxes should not be inside of the ESD protection area. As said before, there are special boxes available made of specific plastics. They have they have a specific surface resistant most of the time in the area of mega ohms. That means if you charge your box and put it on a table, then it can be discharged over time and no high voltages appear in your ESD protection area. So don't use any cartons in this area. Yeah.
Okay, thank you. Then I think we have time for one last question. So, next question. What are the differences between superresistors, resistor, or T4S diode, the drawbacks and benefits?
Okay, yeah. So I guess it's more kind of naming, because suppressors, our ESD suppressors, it's our naming for our series. Our ESD suppressors are simply said varistors, but they are specified for ESD purposes. That means you have a varistor, but in datasheet it is mentioned that he is capable of handling ESD events. And at the end, so we are looking for the differences between varistors and TVS diodes, and therefore TVS diodes are simply said much smaller. You have more of them in one package, but they are made of silicon, so at the end they are not able to handle that much energy than a varistor can do. So if you have or if you know the device should be able to handle a little bit more energy, then the varistor would be the better way. But at the end, a varistor, it depends on the voltage you want to protect. The lower the voltage level is, the higher the capacitance of the varistor is. And if your bus structure is not able to handle this high capacitance, you have to take a TVS diode. On the other hand, varistors can handle much more energy. They are switching in the same speed, more or less. They're a little bit faster than TVS diodes, so they can handle those short time events. But you need simply set more space on your PCB.
Thank you. Okay, then I would say we are finished with the session. Thank you, Christian, for your presentation and also for the answers. Thank you for your attention. I hope you enjoyed it, and hopefully we see us on the next session of our digital weekdays. And then I would say thank you and goodbye.
See you.